Module 14 is on the transport layer of the TCP/IP stack and the corresponding OSI model. In this module, we'll compare the operations of the transport layer protocols in supporting end-to-end communication, and we'll review the two main protocols used at this layer, network layer, namely the transmission control protocol and the user datagram protocol, and how they operate. The transport layer is responsible for logical communications between applications running on different hosts. And it's the link between the application layer and the lower layers that are responsible for passing data across the network. As we see that the TCP/IP stack is a four-layer model of communication and built on the network access layer that is responsible for all of the OSI model characteristics of the physical layer and the data link layer. So it's we have down at the bottom the network access layer responsible for both the physical layer activities, the cables, the connectors, the light waves, radio waves, electronic pulses, all the physical characteristics of how things are connected and data is physically moved. Then we have the data link layer, which is in charge of framing the data and the media access control methodology, and built upon that is your network layer of the OSI model, which corresponds directly to the internet layer of the TCP/IP stack, which is in charge of the logical or hierarchical addressing scheme that's typically implemented through software, through the network operating systems. And we look at our most common internet layer protocols are the Internet Protocol version 4 and Internet Protocol version 6, which we've covered in previous modules. So we're working our way up this protocol stack here as it relates to either the TCP/IP model or the OSI model as a 7-layer model. And we're now moving into the transport layer. And at the transport layer, it's called the transport layer in both the TCP/IP and OSI models. This layer is responsible for, as we said, the logical communications between applications on the different hosts. So end-to-end flow and error control between the two devices communicating. As we know, we use computers nowadays and they're multitasking devices. So the phones we use, the smartphones we use, the tablets, the laptops and computers and all these different networked devices we'll be utilizing multiple different applications. We may be browsing a website or multiple websites. We may be using instant messaging applications or online video conferencing applications, sending email, transferring files, doing downloads. Multiple tasks are being simultaneously managed, and that data stream that goes to the network is being segmented. And so the computer has to identify these different conversations and track these different conversations as they leave and come back to the computer. And this is the job of the transport layer. It uses extra header information to identify the incoming and outgoing conversations. And it uses the process of segmenting the data to enable it to break the conversation into pieces and to resegment them at the other end. These data streams, then, these conversations, as they get put out onto the wire, hit the network and are interleaved with other people's communications on the network. So there has to be additional information to identify these segments of information, these chunks of information, and to track the individual conversations. So as we look at the TCP/IP stack here, we'll be utilizing some kind of application, like say we're using Firefox, and we're using Firefox here as our web browser to browse the internet. Well, that application actually, before it makes a request to the web server out on the internet, it needs to resolve the name of the website that you're going to, for instance www.walmart.com, to an IP address, and that service is the domain name service, or domain name system, DNS. And once it queries the DNS server and gets the response, the IP address of the server you're wanting to communicate, then it can go ahead and issue that web request, and it'll use the hypertext transfer protocol to do that. Well, these protocols at the application layer will choose a particular protocol at the transport layer based on their communication needs. And so dependent on whether you're using the transmission control protocol or the user datagram protocol, these conversations will get different types of service. TCP provides reliability and flow control, and its basic operations, the transmission control protocol, we're going to look at that protocol first. It numbers and tracks the data segments transmitted to a specific host from a particular application. It acknowledges received data. Any unacknowledged traffic can, after a certain amount of time, will be picked up and retransmitted. The data is sequence data that is picked up at the receiving end may arrive out of order, and at that point it can be reordered in the proper order. And TCP provides flow control. So it establishes a flow rate between the sending and receiving devices that's acceptable by both devices. And that way, one device does not overload the other device's capability to receive and understand that information. Now, applications that don't require flow control and sequence data and error control will utilize the user datagram protocol at the transport layer. UDP provides the basic functions for delivering datagrams or segments between the appropriate applications with very little overhead and data checking. UDP is considered a connectionless protocol. So what we talked about with the transmission control protocol and providing flow control and error control and those things those are considered connection-oriented services, guaranteed delivery of service, and guaranteed delivery of packets between the hosts. UDP is connectionless and does not guarantee delivery. It's a best effort delivery protocol, so it provides best effort delivery. There's no acknowledgement that the data is received at the destination, and there's no retransmission of data that has been lost. So UDP is typically used by request and reply applications where the data is minimal and retransmission can be done quickly, and that retransmission can be done via the upper layer application layer protocol. It doesn't require that service from the lower layers of the TCP/IP stack. If it's important that all the data arrive and that it be proper processed in the proper sequence, then you're best to use the transmission control protocol at the transport layer. So these application layer protocols, such as voice over IP, IP telephony, the domain name resolution service, or DNS, email, the simple mail transfer protocol or the internet message application protocol, and World Wide Web applications, the hypertext transfer protocol or the secure version of that. These application layer protocols are written to utilize the one or two transport layer protocols based on their needs. So in this, as you see here, voice over IP or IP telephony is a streaming audio, and it needs fast, low overhead characteristics. It doesn't require acknowledgments or resending of lost data, and the delivery of data comes as it arrives. There's no need to resequence data. So these low latency real-time applications prefer to use the user datagram protocol for its low overhead and low latency, meaning their fast delivery and without a lot of delay. It wouldn't make sense for an audio stream to retransmit things that happened in the past. They're no longer relevant. Whereas a file transfer or an email or downloading a web page, you want to get every bit as it was transmitted. So it's important that it's a reliable delivery service, that the data is acknowledged, any lost data or data that was not received needs to be retransmitted so that it is received, and it's put in the proper order. So you can see the difference between the user datagram protocol and the transmission control protocol at the transport layers, the types of service they provide. So let's kind of focus more on the transmission control protocol. The transmission control protocol is a connection-oriented protocol, meaning we establish a session between the two hosts, the source and destination devices, prior to forwarding any traffic. This is often termed a virtual circuit being established between the two devices. For many reasons, it's possible for a segment to become lost or corrupted as it's transmitted over the network, and TCP ensures that each segment that's sent by the source arrives at the destination. So you have reliable delivery. And there may be multiple routes between two devices. You know, if they're passing traffic through the internet, there's multiple routes between those hosts. And they have different transmission rates and delays, so data conceivably can come in the wrong order. And so the transmission control protocol will provide for reordering of data as it's received to ensure that it's in the proper order. And network hosts have limited resources, memory, processing power, network interface speeds. And so when TCP is aware that these resources are being overtaxed, it can request that the sending application reduce the rate of data flow. And that provides for flow control, that one host does not exceed the other host's ability to interpret the data and receive the data properly. So as we look at the transmission control protocol, we will take the data that comes down from the application layer. It will become everything that comes down from HTTP or TFTP or SMTP, you know, those application layer protocols, becomes the data field of a TCP segment or a UDP segment or datagram. Now, so this becomes the data portion. And then TCP, in this case, we're going to focus on TCP for a while. It will append fields on the front of that data. Okay, and the TCP header is a 20-byte header. It is broken into the two main fields of the header are the source and destination ports. They identify the application, the sending application and the receiving applications or services. The sequence number is for the ordering of the segments in the proper order. As we are receiving data, we will acknowledge the receipt of data so that we identify if data has been lost and needs to be retransmitted. There's a header length field which identifies the length of the header. There are some control bits, which we'll get into the specifics of some of these bits here. There's a window size field which establishes how much data can be sent before the sender has to wait for an acknowledgement. And so that's managing the flow rate, flow control between the hosts. There's a checksum which will check the integrity of the data to see if anything's been corrupted on transmit. And there's a description of the different fields. As we mentioned before, TCP handles all tasks associated with dividing the data stream into segments, providing reliability, and controlling data flow and reordering these segments. So applications like the file transfer protocol with moving files, downloading and uploading files, hypertext transfer protocol for web traffic, simple mail transfer protocol for email, sending email, secure shell for remote terminal sessions. These are all applications that require these services from the transmission control protocol at the transport layer. That data then gets handed down to the Internet protocol for addressing and routing services. Let's turn our attention specifically to the user datagram protocol. The user datagram protocol is a streamlined protocol, and the data does not provide the same services that the transmission control protocol does at the transport layer. For instance, data is reconstructed in the order it's received. So it is not reordered. There is no reordering of data. Any segments that are lost are not resent. There is no handshaking up front. There's no virtual circuit establishment with the user datagram protocol. And the sending host is not informed about the resource availability of the receiving host. So you can see that there's no flow and error control, end-to-end flow and error control between the two hosts. It is considered connectionless, best effort delivery. So with that in mind, the UDP header that gets appended to the application data that's passed down from, say, the domain name service, or DNS, or the trivial file transfer protocol, or DHCP. There are a variety of application layer protocols that utilize UDP. And when they pass their data down, it's going to get appended with a UDP header. Now you can notice that instead of a 20-byte header, it's only 8 bytes. So it has lower overhead, and it introduces less overhead than what TCP had. We have the two main fields that are important for both TCP and UDP, and those are the source and destination ports, identifying the applications or services on each host that are to process the data. We have a header length field and a checksum to check for integrity of the data, that it hasn't been corrupted. But that's it. So you don't see any windowing, no sequencing, no acknowledgments. All of that is foregone in the, and we're looking for low overhead, low delay, and best effort delivery. So as I had said, things like the dynamic host configuration protocol, DNS, simple network management protocol, trivial file transfer protocol, voice over IP, video conferencing applications, real-time streaming type activities or network management activities, or name resolution, or IP configuration protocols. They utilize the user datagram protocol because they don't require the TCP/IP stack to provide reliability or flow control or anything. They go for a low overhead, fast service from the TCP/IP stack. Now, if an application like the trivial file transfer protocol up here, you're moving files between hosts, well, you do need those files intact. And instead of having the transport layer protocol providing the reliability, TFTP has its own built-in sequencing and flow control characteristics built into the application itself. So any applications that don't require the TCP/IP stack to provide those kind of flow and error control services, like SNMP and TFTP, for instance, they will provide that service through the application layer protocol and not down at the transport layer protocol, at the transport layer. And some of these other applications are transmitting very small amounts of data, just simple queries and responses, and they don't require sequencing or acknowledgments, that sort of stuff. Port numbers. So we've talked about port numbers. They are a 16-bit number. So in binary, they consist of 16 ones and zeros, a string of 16 ones and zeros, and they are used by TCP and UDP to manage multiple simultaneous conversations, multiple web connections to different websites, using different applications at the same time, like transferring a file while sending email, while instant messaging, that sort of thing. Each one of these activities is considered a separate conversation and will be tracked with different port numbers on both the source and destination host. These ports are added as fields onto the data. So here's our user data from the application layer. This is coming down from your application layer protocol, HTTP, SMTP, etc. We're appending the port numbers onto the data in your segment header. Then at the transport layer, this is being appended to the data. After we've segmented the data, appended the port numbers and the other fields at the transport layer, this information gets passed down to the network layer or the internet layer. So I'm going to say I for internet layer of the TCP/IP stack. That would be the network layer of the OSI model. And the logical addressing is put in. So your source and destination IP addresses are appended along with the rest of the information in the Internet Protocol header. That then is passed down, these packets. This is considered your packet header. This is considered your segment header at the transport layer. And then it's passed down from the internet layer down to the layer below at the data link layer of the OSI model, or the network interface layer. I'm going to say NI for network interface layer of the TCP/IP stack. And we're appending the physical addressing, the source and destination media access control addresses in that 12-digit hexadecimal number that is correlates to your network interface card. Okay, so you can see the varying levels of addressing that take place. The levels of addressing on a link-to-link basis on your local network or your local LAN, then the addressing that is routable and can go from network to network and across the internet. And then the port numbers are another type of address that's identifying the conversations. And once the data reaches the appropriate host, these port numbers are used to route the data to the appropriate service or application. Do I go to my web browser? Do I go to my Outlook, my email client? Do I go to my instant messaging app? That's what the port numbers will identify. The combination of an IP address and the port number are what we call a socket. So you'll see an IP address colon a port number, and that's what we identify as a socket. And that will allow the data to be routed to the appropriate host on the internet. And once it gets to that device, the port number then picks up and routes it to the right service or application. So you can see here a computer sending data to a server out on the internet or out on the network. So in this case, we're using local addressing, private addressing. So this would be a device, a server on the same network. And we see a communication going across. Here's the source MAC address, source IP address, and then you see the source port number. And they're talking, this computer's talking to a server on the network. This would be the destination layer 2 address, the destination layer 3 address, and here's the destination port number. And this is for the file transfer protocol. So if we're using a FTP client talking to the server. And if we bring up a web browser and web browse to a page on the server, that's going to go to the well-defined port number 80 for web traffic. And the source of the traffic will identify it with a random port number. You see here 1099, for example. Okay, so we have different ranges of ports, TCP and UDP ports. The first set of 0 to 1023, they're known as the well-known ports. These well-known ports, like port 80 for web browsing, port 25 for SMTP, port 22 for secure shell. There are a variety of well-known port numbers that computers and servers listen to, and when they receive data on these ports, they hand them to the appropriate service. Now, vendors of equipment and software can register their applications with the Internet Assigned Numbers Authority and have registered ports. These are network applications that are registered out on the IANA and have these registered ports available for particular applications out on there. So, for instance, for central authentication through Radius services, Cisco has registered port 1812 for that purpose. And so again, these may be used as destination ports when a client talks to a server. Now, the client will identify its source port when it communicates with a server in utilizing a random port number. And it'll randomly select a port number, usually from the dynamic port range or private port range. These are called ephemeral ports, and they're dynamically chosen by the client during the conversation. So just think of it as a client may talk to two different web servers. And for the destination port on both conversations, it'll be port 80, so the servers know to give it to the web service. But on the source side, it'll be a random port, so that when the traffic comes back, the client knows which conversation it goes to, which web conversation it goes to. You wouldn't want to use port 80 for the source port on both conversations, because then you wouldn't know, the conversation coming back belongs to your conversation with www.kmart.com, and the other one, traffic conversation, identifies to walmart.com, for example. So you see some of the well-known port numbers here. In these ones, you should commit to memory. These are the most common ones that we see, and the reason we want to remember these is that when we're setting up firewall services on routers and dedicated security appliances, we're going to be allowing or disallowing certain traffic by what we call access control lists, and these packet filters will inspect the traffic stream and look to these TCP and UDP port numbers to identify if they're going to allow that traffic through the device. So we see here for the file transfer protocol, both control and data traffic use ports 20 and 21. Secure Shell and Telnet for remote terminal sessions use ports 22 and 23. 25 is dedicated for simple mail transfer protocol, email, sending email. Port 53 is your DNS services, your domain name service, and it can utilize either UDP for querying or TCP for transferring zone information between servers. The dynamic host configuration protocol for assigning IP information on the network uses port 68 on the client side and 67 on the server side. The trivial file transfer protocol, TFTP, uses port 69. The World Wide Web protocol, HTTP, utilizes port 80. And the secure version of it uses port 443. We see getting email through either IMAP, the Internet Message Access Protocol, or POP3 use ports 110 and 143. And your simple network management protocol for monitoring devices on the network and managing them uses port 161. On your computer, you can drop to a command prompt, and from the command line interface, you can do a netstat or a netstat -a, and you'll identify the active listening ports and conversations that you have on your computer. And so you see here, this is an example of a Windows socket, for example. Here's your IP address, your port number. Your TCP port number in this case. This is your network basic input-output service utilizing this port 3126. That's the random port number, and then for the well-defined port number, it actually puts in a keyword there. And instead of putting port 80, it puts HTTP here. You can use different netstat. If you put a netstat -a or R, there are different switches you can provide to the netstat command to give you different information. Now that we have a understanding of the fundamental difference between TCP and UDP and how they operate, either connection-oriented service through TCP or connection-less service through UDP. Let's kind of dig a little deeper in how the transmission control protocol establishes these, provides the connection-oriented guaranteed delivery of service. So we see here with the TCP server processes, we have multiple clients making requests to the server. So you see here we have a client 1 making an HTTP request to the server, and it's identifying the random port number here as 49152. It's sending HTTP request to the server on port 80. So this request goes up to the server and is received on port 80. Now the server then, when it responds, it's responding using its port number 80, and when it responds to the client's IP address, it will put reverse the port numbers. So what was the random source port when the client spoke to the server, it now becomes the destination port. So when the server's talking back, it talks back to client 1's port 49152. And it establishes this conversation so that future packets and segments coming to the server on port 80 with a source port of 49152, it knows that it belongs to this conversation between these two hosts, client 1 and the server. When client 2 makes an email request or is sending an email to the email server service, it's identifying a random source port of 51152. And it's sending to the server's well-defined or well-known port number of port 25 for the simple mail transfer protocol. So that initial request goes up to the server from client 2. It's received on port 25. That's the destination port when the client 2 is sending the data. The server then takes and reverses the port numbers from the destination port now becomes the source port. When it's talking back, it reverses the port numbers, and what was the destination port is now the source port. What was the source port is now the destination port when the server responds to client 2's conversation. And so then future packets coming to the server on port 25 with client 2's IP address, that socket, will be identified to the conversation between the server and client 2. Okay, now when these TCP conversations start, we start with what's called a three-way handshake. In this three-way handshake, and I'm just going to put H for handshake here. This three-way handshake establishes the virtual circuit before the actual email sent or the actual web request is sent, before any data is sent. It identifies that the receiving device is available, that it's up and operational and listening on that port number on the network. So the client here, here's our client making a connection to the server, and it starts by sending a synchronization packet. Okay, this synchronization packet goes from the client. It establishes a starting sequence number, sometimes referred to as a relative sequence number. This is saying, hey, I'm starting with byte 100. Here I'm starting that sequence number at 100, and its control field is set. The synchronization bit is set to 1 in the control field of the TCP control field part of the TCP segment header. And the server receives that and receives the synchronization. It then talks back to the client and says, hey, I'm acknowledging your sequence number of 100, and I'm ready to receive byte 101. Okay, now I'm going to send you my own sequence number starting at 300, and I've set the synchronization bit to 1, and I've set the acknowledgement bit in the control field to 1. So it acknowledges the synchronization from the client. The client gets that SYNAC, synchronization acknowledgement, and then it acknowledges the acknowledgement. So it goes ahead and says, okay, we're going to establish the connection. I'm sending byte 101. I've received your sequence number 300, and I'm ready for 301 from you. And I've set the acknowledgement bit to 1 in the control field. So this is the three-way handshake that starts before, and it establishes what's called the virtual circuit between the client and server before the data transfer occurs. So this is the reliable communication process. It first establishes both hosts are ready to go and establishes the parameters for the conversation before it starts with the actual data transfer. Okay, and termination. So once they send the data and the conversation is finished, they'll finish the conversation and terminate the conversation. So again, in the control field part of that field of the TCP header, the fin flag will be set to 1. When computer A is ready to terminate the session, it'll send a finish flag to B, the server. In this case, say this is the client and this is the server. And then the server will acknowledge the receipt of that, and the client acknowledges the acknowledgement. And at that point, the conversation is terminated. So again, the three-way handshake makes sure that the destination device is present on the network, that it's actively has an active service, listening and accepting requests on the destination port number that the initiating client intends to use. The three-way handshake is, once that's completed, then the data is transferred between the client and the server, the two hosts on the network. And after the completion, the communication is completed, the sessions are closed, and that means the connection's terminated. So we've been talking about the control field here, and it's composed of 6 bits. Some of them that we've been focusing on are the acknowledgement bit. We've been talking about the SYN bit, the synchronization bit, and when we're done with the communication, the finish bit or flag. There's a little video on the TCP three-way handshake that'll go through establishing and terminating connections, TCP connections. Let's look at TCP reliability and flow control in more depth. TCP can also help maintain the flow of packets so that devices do not become overloaded. There may be times when TCP segments don't arrive in the proper order as well and need to be reordered or reassembled into the original order they were sent. Sequence numbers are assigned in the header of each packet to achieve this goal. So as the computer A here sends information to computer B on the other network, you see alternate paths that can be taken to get there. So these segments that may come through, there are different delays and bandwidths associated with these different connections. As the segments are transmitted, they may be received out of order. So you see here we receive segments 1 and 2, and all of a sudden we've received segment 6, segment 5, etc. These segments can be reassembled and reordered so that the conversation is put in the right context at the receiving end. Here's a quick video demonstrating some of that. And no matter how well designed a network is, data loss occasionally occurs. There may be a switch or a router or a firewall, some network appliance that along the path may become congested and have to drop some packets. You may also experience corruption due to electromagnetic interference, EMI, or RFI, radio frequency interference, and that those corrupted bits will be dropped or discarded, and so you'll have a loss of data. So in the conversation from computer A to computer B, we see segments 1 and 2 being transmitted, and then you see segments 3 and 4 being dropped for some reason along the pathway to the recipient, computer B, and the rest of the segments coming in through segment 10. Well, computer B will go ahead and it's successfully received segments 1 and 2, and it will acknowledge that fact by saying, I'm ready for segment 3. And computer A then will look and say, okay, well, I'm going to start retransmitting everything again after segment 3. Even though I've sent segments 3 through 10, computer B is just letting me know that it successfully received segments 1 and 2, and it's ready for the third one. So segments 3, 4, all the way through 10 will be retransmitted again. And there's a duplication that occurs because segments 5 through 10 were already received, but computer A is going to resend them anyways. Now that's not very efficient, so there is an option for hosts to utilize selective acknowledgments, as long as both hosts have that ability, support selective acknowledgments. We see the same process of segments 1 and 2 being sent from computer A there successfully, and then 3 and 4 getting dropped along the way, and successful receipt of segments 5 through 10 as well. And what computer B will do is, after a period of time, there'll be a timeout period while it's waiting to get all the packets. It's picking them up, and it will identify that segments 3 and 4 have not been received. So it'll give an acknowledgement saying, hey, I received 1 and 2. I'm ready for segment 3. However, I did receive segments 5 through 10. Okay, so computer A will go backtrack back to starting with segment 3, send segments 3 and 4. It knows then, hey, 5 through 10 were already sent. I don't need to duplicate that effort. And then it will begin again with 11, 12, and that window size hits, and a window size, say, of 10 in this case. And then on the 12th segment, 2 plus 10, it'll stop and wait, and computer B sends and says, hey, I'm ready for segment 13 by acknowledging 13. There's a quick video showing data loss and retransmission, how that works in TCP/IP. So TCP, the Transmission Control Protocol, also provides mechanisms for the flow control, and by setting a window size. So that is the amount of data that the destination can receive and process reliably. So let's say that during the handshake that our maximum window size is 10,000 bytes. And that basically means that computer A then will be allowed to send 10,000 bytes unacknowledged before it has to stop and wait for computer B to acknowledge receipt of some of that information, some or all of that information. So this will help the communication process by not overloading the destination with too much information. So we see here also in that initial handshake will be a maximum segment size that will be negotiated. And we'll talk a little bit more about that here in a second. So basically each bundle, each segment size is going to be 1,460 bytes. So we're sending segment 1, of which contains 1,460 bytes, and computer A then sends segment 2, and receive the next batch of 1,460 bytes, totaling 2920 here. Computer B, somewhere in between those 10,000 bytes as it's receiving, it can send an acknowledgement back and saying, hey, I received the first 2,920 bytes. I'm ready for 2,921, byte 2921. And we're keeping our window size at 10,000. So it resets the window size, and I add 10,000 to 2920, and that's my new window here. And so I can send again all the way up, keep sending data all the way up until byte 12,920. Somewhere in between that sequence, computer B is going to send another acknowledgement back and reset the window size. And that establishes the flow rate. So you're getting an idea of how we can detect errors, with the sequencing and acknowledgments, and then the window sizing providing for flow control. And that maximum segment size is usually computed as by looking at the Ethernet framing. So that's your typical frame format on most networks, especially LAN networks. And so when we're using IP version 4, it'll vary between IP version 4 and IPv6 because the header links are different. But if we look at an example of an Ethernet network, a LAN network, and utilizing the Internet Protocol version 4, we're going to base our calculations on Ethernet, maximum Ethernet frame size, which is 1500 bytes by default. That's the MTU for Ethernet, maximum transmission unit. And when we add on our IPv4 header, that's 20 bytes, and our TCP header, another 20 bytes. That should be a minus 40 here instead of 60. They made a mistake in the slides here, but that'll provide for that maximum segment size of 1460. And we, as the communication between A and B happens, we're sending these segments. Some may be lost, and in the event that computer B acknowledges back and computer A recognizes a loss of data here, computer A will back the window size down. So, and that is to if there's congestion being experienced somewhere in the path between A and B, by backing the flow rate down, that will help alleviate the congestion. So, in the previous example, we were looking at a window size of 10,000 bytes. Well, if we see some congestion being experienced in drop segments along the way, what TCP will do is slide that window and cut it in half. It's and then the window size will go down to 5,000 bytes. So now computer A can send up to 5,000 unacknowledged bytes without having to stop and wait for an acknowledgement from B. And that way, the two hosts can help reduce congestion that's being experienced in the network. There aren't a whole lot of new things or detailed information that needs to be covered about UDP communications because UDP does not establish a connection up front. There's no virtual circuit establishment before sending data. It's best effort delivery. It's connectionless, and so it has the only thing we can really say here that benefit is low overhead versus the reliability that TCP had. So if you're looking for guaranteed delivery of service with error and flow control and reliability, you go with TCP. If an application layer protocol does not want that from the TCP/IP stack and prefers to go low overhead, less latency approach, we use the user datagram protocol. So just to again say, the data that's being transmitted across the network may have multiple pathways, and as these segments are sent, they may be received out of order. And with UDP, that's not a concern. It's just going to deliver those packets, and the host from UDP, that portion of the network stack, is unconcerned about out of order datagrams or segments, and they're not reordered, and the loss of datagrams are not resent. So that specific functionality that we described in more detail in regards to TCP is not there with UDP. However, what is consistent between TCP and UDP is that when the clients establish a connection with the server, two hosts are communicating, client to server in this case, that will utilize port numbers. And those well-known or registered port numbers will typically be your destination port numbers. As the initial conversation goes, the client's going to utilize these well-defined port numbers, either well-known ports up through 1023 or those registered port numbers through the Internet Assigned Numbers Authority, up through 49,000, and the server then knows what application to or service to hand those segments to, or those packets. And then when the server communicates back, it's going to turn around the port numbers from what was the destination port number now becomes the source, and it talks back to the client's randomly generated ephemeral port number, that dynamic port number. And that's how the conversation continues back and forth between client and server. And again, client 2 coming up and initiating an authentication request through Radius. Prior, it went to port 1812, so client 2 over here was using Radius to authenticate a username and password, and it sent it to destination port 1812. Now when the server talks back, that becomes the source port, and coming back to the client, the destination port is the randomly generated port number that the client used on the initial communication going up, right down here. And that takes care of Module 14. Let's take a look at a typical web conversation using the Wireshark protocol analyzer application to look into the details of the conversation and relate it to our discussion in Module 14. Before I do this, I'm going to bring up my network and internet settings, and I'm going to disable IP version 6 on my wireless adapter. So to do so, I'm going into my wireless adapter protocols properties and turning off IP version 6. This is just to enforce that my computer is going to use Internet Protocol version 4 to communicate, and when I'm capturing things, it'll be just that one protocol being captured and not IP version 6 as well. That'll be less confusing in the protocol capture. And it'll look more like what we saw in our previous discussion. So I'm going to, now that I've forced my computer to just using only IP version 4, I'm just bringing up a web browser, Google Chrome in this example. And before I actually go to a website, I'm going to start my Wireshark packet capture. So remember, Wireshark can be downloaded for free at wireshark.org. And I've installed it here, and I'm making sure to capture on my Wi-Fi adapter. All right, and I'm going to bring up my browser and go to that website we were talking about in our previous discussion, www.iana.org. And I'm capturing that web request and then the response that the server's providing. And I'm just going to stop the capture at this point, and we'll diagnose that short conversation. Notice how Wireshark has captured over 900 packets in that short amount of time. Our web conversation first starts by putting in www.iana.org in the web address bar, And our web browser then has to convert that fully qualified domain name to an IP address. That's using the domain name service, or DNS. So I'm going to the protocol header, of the header for the protocol column, and I'm just organizing it by in ascending order, and I'm scrolling to the top. Whoops, let me go ahead and go in ascending order and scroll to the top here, and it'll list all the protocols captured in alphabetical order and ascending order. So where I'm getting at is I'm keying in on the DNS query that is going off and trying to resolve that name to an IP address. So you see here packet 219, sequence number 219 there. It is a query going from my computer at 192.168.0.25 to one of Comcast's DNS servers. And I actually have both a primary and secondary DNS server listed in my IP properties. And so my computer is issuing two queries out to resolve the name www.iana.org to an IP address. And maybe I can go ahead and zoom here a little bit so you can see that. Let me zoom in, and you see the query there. All right, and what comes after the question then should be a response back from Comcast DNS server. So I see here comes back my query response, and let's see what the answer is. I'm going to expand the domain name system information down here, and you'll see, let me go ahead and magnify here, that we got a result of 192.0.32.8. Now that's a public IP address. The private ones that start 192.168 are private, but they have to have a 168 in the second octet. So this is actually a public address, and it's hosting information from the Internet Consortium for assigned names and numbers. That's where iana.org moved to. So we see that it was taken over by the Internet Corporation for Assigned Names and Numbers some years ago. And anyways, here is the IP address of that website that we're hitting then. So I can key in on that conversation. I now know the address of the website that I'm visiting. Let me zoom back out here, and we're going to try to then find, I'm going to reorder the packets back in their sequential order, going to column 1. That we are sitting at frame 226. So here we are at 226. We just got the response back, and now you see my computer issuing in frame 227 here. It's issuing from my computer at 192.168.0.25 to 192.0.32.8, a synchronization. And actually you see a few of them coming off here, these synchronization packets coming off. There's actually a series of 3 of them. And then you're starting, that's the first leg of the 3-way handshake. So this first one here, let's go down in and just kind of look at what's taking place here. So my web browser now has the IP address of the website, and that's 192.0.32.8, and it initiates the synchronization. Starts with the 3-way handshake. So here's the first leg of that 3-way handshake that we're seeing here. Let me see if I can scroll over a little bit for you, and you'll see here It's going to the web server. Now, the 54625, that's the random port my computer has associated to the conversation. And 443 it's going to the well-defined port number for HTTPS, the secure version of HTTP. And you see the SYN, it's a synchronization, TCP SYN. And starting with relative sequence number 0, setting, trying to negotiate a window size of 64 to 240 with a maximum segment size of 1,460 there. And then you see also, if I'm going to zoom back out of here a little bit, you can see that the selective acknowledgments is permitted as well. So, all right. And then next you're seeing the server responding. And the server is now responding with the SYN-ACK. So you see that right there on this packet. And it's coming back. And so it's actually in response to this one here, right here on going to port 80, the first one, HTTP. Then you see it coming back on that port 80, and it's doing the SYN-ACK there, setting its own sequence number, relative sequence number is 0, and acknowledging that it received sequence number 0 from my computer and saying it's ready for the next one, 1. And then it's sending, so that's the SYN-ACK that's going back to my computer from the server. And now my computer is coming back to the server, 192.168.0.25. That's my computer talking back to the server here. And it's coming from my random port number back to port 80. And you see the setting the sequence number, was 0. It's been incremented to 1, and it's acknowledging that it received sequence number 0 from the server, and it's ready for the next one, and trying to negotiate that window size. And once that has taken place, then you see the hypertext transfer protocol, HTTP, get into play. And here it's making a GET request for the default web page. So you can see how in Wireshark it's showing us that conversation as it occurs, and you're getting a glimpse in as you expand the packet contents. You can view the header information and view those source and destination port numbers as we had talked about in our discussion. And here it's using HTTP instead of HTTPS there. You see those relative sequence numbers, the raw sequence numbers, the acknowledgments, the header length fields. All of that information is contained in the field headers. And Wireshark lets you take a glimpse into that conversation of that captured conversation. So hopefully seeing that in Wireshark helps relate everything that we just discussed in Module 14.